So we're going to do kind of like this first part's kind of like a review of a lot of your vocabulary, but just to get your brain back into, wow, serious yawns everywhere. You guys are sleepy. Get your brains back into it. So, first one, circles are named using what? How do you name a circle? A center point, perfect. Okay, so the circle at the right would be called circle A, awesome. Lines that intersect with circles can intersect at 1 or 2 points. All right, so lines that intersect circles in 2 points is called a what? Begins with an S. Secant. Beautiful. Okay, so which lines in my circle are going to be examples of secants? CG is going to be a secant. Perfect. EF, because it goes all the way through. And do we have any other ones? All right. A chord is part of a secant, and its endpoints lie on the circle. Okay, so I should have done this in a different color. So here's my chord. That would be CD, right? Because I have 2 endpoints. Okay, question for you. If the definition says a secant intersects the circle at 2 points, does the chord intersect at 2 points? It intersects it right here and it intersects it right there, right? So could a chord also be considered a secant?
No, because secants, like, chords are at chords endpoints lie on the circle, whereas secants
go all the way through. And that definitely is, and I agree, that definitely is, that's what distinguishes between the two. Technically, a CD and a chord are considered secants, but a chord better describes them because it's more specific in that you know it doesn't keep going on, it's just boom right here. Okay? All right, diameters are always chords. It says their endpoints lie on the circle. But chords are only sometimes diameters. CD is a good example of that. Okay? So we have AB is a chord. CG would be a chord because that's a diameter. And CD is a chord. But only one's the diameter, which would be our CG. Good with those? All right. What's the line that intersects the circle at exactly 1 point? What's the name of that? What? What was the line that intersects only in 1 point? Tangent. Great. And the point that it intersects it is the point of tangency. Which line is, back to our example up here, which line is tangent? No, because AB intersects here and here. BH, the one here, right? You gotta have 2 letters for the line. So BH is tangent. The other thing too about your tangent lines, they're always gonna be outside the circle. Okay? What is the point of tangency on BH? B. Absolutely. So B is the point of tangency. Okay? Tangents are always perpendicular to the radius. Okay, which makes it super helpful. So here's my tangent line. This is my radius, which means angle S is going to be 90 degrees. So if SR is 28, ST is 45, and I want to find out what RT is. How can I go about doing that? Pythagorean theorem, absolutely. So 45 squared plus 28 squared is going to give me RT squared. Okay, and so my numbers, I got 784 and 2025 when I square it, which gives me a total of 2809. Everybody with me so far? All right, when I take the square root of both of those, that means that RT is 53. So my whole length here is 53. How do I find what UT is? Just the part of the line outside of the circle. Why are we, that's perfect. Why are we subtracting 28? Because UR is my radius. So 53 minus 28. So U2 ends up being 25. Perfect. Good. Leah, where did I lose you? Sure?
Yeah.
Okay. All right. I threw a proof in there because you love your proofs so much. All right, so we have BD and CD, whoops, helps if you can see, are tangent to the circle. And I want to prove that BD is congruent to CD, okay? So if I connect point A to D, possibly what kind of triangles did I just create? Not specific, like, do you could they be congruent? Possibly. All right, so let's look at what we know. I know that BD and CD are tangent. What's my justification? Or reason? Given. Perfect. Okay. I know that AB is going to be congruent to AC. How do I know that? Beautiful. So, radii are congruent. Love it. I know that AD is congruent to AD. How do I know that? Because it's the same, but what's that property or that theorem? Reflexive. Perfect. See, look at you guys. All right, reflexive property. Okay, measure of ABD, so ABD and ACD are 90 degrees. How do we know that?
Tangents make a tangent surface.
Absolutely. So it's just in a definition of a tangent line. Perfect. Okay. So two triangles are congruent with the right angles. Technically, this is the hinge leg. We talked about this a little bit a couple weeks ago, but technically it's that. So, if BD is that, if the two triangles are congruent, that makes BD congruent to CD. How do we know that? Beautiful. Congruent parts of congruent triangles are congruent. Beautiful. Which means then that we can say that if I have two tangent segments to a circle that share the same external point, which in this case was D, that was our external point, they're congruent. And that is a real helpful theorem. Okay, so for example, BD and CD are tangent to the circle. So how can I solve to find out what BD is? Yeah, since they're equal, we just proved that. 4W plus 2 is going to be 6W minus 12. So when I solve for W, W is going to be 7. But it's asking what the length is, so I have to put my 7 back in. So BD is going to be 28 plus 2. Oops. So BD equals 30. Good so far? Alright, which is super helpful if I need to know, so now I know that BD is 30. If I know AB, or my radius, is 18, it's asking for calculating, let's see, let's use, I want to find AD. How can I do that? Pythagorean theorem, best thing in the world. So 18 squared plus 30 squared is going to give me my AD squared. Oops. Alright, so when I do my calculations, I'm going to get 324 plus 900 equals my AD squared, which add together to 1224. And when I square root that bad boy, AD gives me very helpful when we need to find different lengths and stuff. Good so far? Alright. Concentric circles is what these are called. Okay? And if you have which are examples down here. Your concentric circles are where this circle lies within here. So they're not congruent, but they're going to be what? Similar, exactly. Okay. And we can say that they're congruent if they have the same radii. And so a lot of these are helpful when you have trying to find out, like, for the whole big. So if EB, this one right here, is 5x minus 6, and we know AD is 3x plus 8, that means I know that they're equal to each other, right? Would you agree with that part? And remember, the whole goal, and what I'm trying to do is calculate out BC. Okay? So, if I solve for x, I'm going to get 14 is equal to 2x, so x is going to be 7. That means that I can find this smaller radius which is going to give me my 35 minus 6, so 29. So how can I use that to figure out what the whole thing is? What do you think?
You could multiply it by 4 because there's 4 radii from the radius of the big circle to its point.
3. Those are all going to be equal, right? All right, so 29 times 4 is going to give me my radius, but I want the actual diameter. So what am I going to multiply it by?
Either do that times 8
Or times it by 2, either one. And that's going to give me my BC. Good? Yeah. All right, so my last one, concentric circles are coplanar. What's that mean? On the same plane, and they share the same center. If you have tangent circles, like these are tangent, it touches in one point on the same plane, but they don't have the same center. Good? Beautiful tangent lines. They are very helpful.